Okay, welcome to the video. So today we're going to be looking at exponential functions, and this is grade 10 technical mathematics. So let's first start off with the definition of what is an exponential function. So a definition says that um, an exponential function is a function, right? And remember, when we say it is a function, it means that it satisfies certain conditions when we check with the vertical line test, right? And so it is of the form, right? Y is equals to A times, right? B all to the power X, right? So B is the only thing to the power X, right? So our inputs now, in this case, are actually X, right? It's X, but it's actually an exponent, right? So every time we put in an input, it is an exponent, right? And then our output is just Y, and then our A and B, we'll talk about it as we go along, right? Or you could have written it in functional notation, right? Where it would have said f of x and f being the name of that particular function. Because you can have a number of functions and they'd say we have f of x, meaning when they talk about f, the function f, then you're talking about this type of function. Or maybe they could mean that you have a function g, which is a parabola, or a function h, which is a straight line, right? So it's just for us to be able to identify which one we are working with at that particular point in time. But here we have f of x is equals to a times b all to the power x. Same thing, right? Now they also say that b is a positive real number. This is quite important. Positive. B, which B is the number that it is this number that we will place here, where we will raise it to x, right? So when we raise it to x, B has to be positive. It has to be positive. And you'll actually realize why it has to be positive maybe later on. But it has to be positive. It is never, ever, ever negative. It is never, ever negative. Okay? It is always positive. B is always positive, and it's a real number, so it can be any number. And then, other than 1, right? Other than 1, right? So it's any positive real number except 1. And also, x can be any real number, right? So x can be any real number. Okay. So recall that f of x is equals to y. It's the same thing, just that it's a difference in notation, right? It's a difference in notation. Okay. So here I've just kind of summarized the definition of what it's saying. F of x is equals to a b to the power x. B is to the power x, right? B is to the power x. This means what? It means with B mustn't be an element, right? Of 0 to 1 union from 1 to infinity. Wait, let me say that again. Maybe let me put in more information, right? So it says B is an element. Elements can also mean to belong to. So they say B, whatever number that we're going to put in as B, it belongs to all the numbers that are in between 0 to 1, but we do not include 0 and we do not include 1. And we add and union, and when we continue, it is from 1 to infinity, but we exclude 1 but 2 all the way to infinity, because infinity is any particular big number, because we don't know what infinity is. Infinity is just a very, very big number. You can think of a trillion, you can think of kajillion, and you can even think of another number bigger than kajillion. So that's why we just say infinity. Okay, so that's what it means. B belongs in between 0 and 1, where 0 and 1 are not included, and we know that from 1 to infinity, it still belongs to B as well, right? Okay, and then we can also see that for x is an element of negative infinity to positive infinity. But when we read it maybe in a more understandable sense, what it means, it says that x belongs in between negative infinity to positive infinity, okay? And obviously we can't include infinities, right? Or another way of looking at it, a shorthand, which is, this is called set builder notation. It means the same thing. These two things mean the same thing, right? Because this is interval notation and this is set builder notation. So now it says x belongs to the real numbers. When we say x belongs to the real numbers, we're talking about all the numbers from negative infinity to positive infinity. And so basically that's what they were saying in words, but we've just put it in a more mathematical sense. Now, we're going to start off with the example 1. Now, we have example 1 where it says y is equal to 3 all to the power of x, right? Now, what is a and what is b from the function, right? So remember, we have the general formula, which is equals to y is equals to ab to the power of x. A times b all to the power of x. So in this case, when we look at this, we can see that a is definitely what? It is 1. And b is 3 to the power of x, right? So it's 1 times 3x, but 1 times 3x is the same as just saying 3 to the power of x. That's why that happened. But there's something that I want you to notice here. Notice that a is greater than 0 and b, since it's equals to 3, it is greater than 1. If b is greater than 1, remember b, what was the condition? It has to be between 1 to infinity or 0 or 1, right? But here 3 is definitely in between 1 to infinity. So it does satisfy the general definition of an exponential equation, a function, right? Okay, so we have that, right? Now let's draw this particular graph using the table method. Now please notice here, we use the table method. I chose to start at -6 to +6. You could have started at -3 to 3 or any other place, but there are just 3 things that needed to be in your table method. You need to have negative numbers, you need to have 0, and you need to have positive numbers. That is exactly what has happened here. We have all the negative numbers, -6 to -1. We have 0 in between them, and then we have all the positive numbers from 1 to 6. Okay, so now I've already calculated the actual values when we put this into the equation, right? So we would have said x is equals to 6, right? -6. So if we say -6, then we would have said 3 to the power of -6, right? So we would have said 3 to the power of -6. And on the calculator, would have given you an answer. Now, try it out first. Try it out first on your calculator. Stop the video right now and then try it out. And then once you've got the answer, come back to the video. Okay, so you've tried it out, right? So it's -6, right? Did you see on your calculator, it gave you a very long list of numbers, right? It was 0, 0, 0,001, and then something all over there. I left out all the other numbers. I kept it to 3 decimal places, okay? So, but please notice something here. -6, right, gives you 0,001. -5 gives you 0,004. -4 gives you 0,012. -3 gives you 0,037. -2 gives you 0,111. -1 gives you 0,333. But then 0 gives you 1, 1 gives you 3, 2 gives you 9, 3 gives you 27, 4 gives you 81, 5 gives you 243, and 6 gives you 729, right? Now, as you can see, when you look at it from -6 to positive 6, what is happening? The numbers are actually increasing very fast, no? Can you see? Just between 2 to 5, 2 was 9, but at 5 it was 243. It increased very fast, right? But when we look the other way, now there's something that's quite interesting here. When we look the other way, the numbers are getting smaller, right? So when you put negative 6, when you compare 0 compared to negative 6, 0 was bigger than 0, 0, which was 1, right? Is bigger than obviously 0, 0.01. 1 is bigger than 0, 0.01. So as the x values got smaller, right? Then what happened? The number became even smaller, but there's something funny that's happening here. Do you notice that 0, 0.001, when you had to round it off, it would be just 0, no? It's true, right? If you look at 0, 0.004 as well, if you round it off, that would be 0. But also you can see 0, 0.012 would have happened the same thing, right? All the way to negative 1, right? X when it's negative 1 at 0, 0.333. When you round that off, that would be just 0, right? But, so there's something that it's telling you here. As the numbers get smaller, right? Or we could say when x tends, and this means tends or going to, it goes to negative infinity, right? Meaning the numbers are getting smaller and smaller and smaller and smaller to negative infinity. What happens? This y also tends to something. It goes nearer to some number. But that number, it never becomes that number. And what is that number? It is 0. So, as x tends to negative infinity, y also tends to 0. Okay, so there's a lesson there. There's something that it's trying to tell you there. As the numbers get smaller, also the y values tend to become even closer and closer and closer and closer to 0. How can you check this? Take your calculator, say put 3, right, all to the exponent negative 10. And then take that number, write it down, see how many zeros after the comma, and then take another number and say 3 to the exponent negative 100. Okay, don't say negative 100, maybe your calculator won't work. Maybe say negative 15 and compare those two, and you'll see that it just becomes 0, 0.0000, and you get more and more zeros, but still there's always something there at the end. But that is basically when we're talking about something that tends towards something. It comes closer and closer towards 0, okay? But there's actually a name for this that we call it by, right? If you have done your hyperbolic function, you would know the name. Okay, but here's the graph. Here's the graph. As you can see, the exponential function, as the x values increase, also the y values increase, right? But when the x values decrease, the y values also decrease. It gets smaller and smaller, right? But it goes nearer, but never reaches 0, right? Now, let's find the y-intercept. So if you want the y-intercept, what do we do first? We say we let or make or put x to be equals to 0, right? And so f of x is 0, and then that's equals to 3 over 0, 3 to the power of 0. But 3 to the power of 0 is just 1, right? So f of 0 is equals to 1. And therefore your coordinate of the y-intercept is 0 maps 1. Is the y-intercept 0 maps 1? And as you can see right there, there we have our y-intercept, which is 1, 2, 3, 4, 5. You see? And this is the x-axis, and that would be your negative y's. Okay, how about our x-intercept? Now, I know when you look at this graph, it looks like it's touching the x-axis. It looks like it's touching the x-axis, but it's not. The only reason it looks like it's touching the x-axis is because this graph drawer, right, because I used a software, it uses lines which are just a bit too thick, right? But mathematically, it knows that it never touches, okay? Now, if we had tried to find the x-intercept, what do we usually do? The method is we let make or put that y to be equals to 0. If we put that in, then it's 0 is equals to 3 all to the power of x. Can this be solved? It cannot be, right? It can't be solved. You can try as much as you can, but 3 to the power of x can never, ever, whichever number you could think of, it could never give you 0. So this is impossible, right? 0 cannot be equals to 3 to the power of x, right? We can't solve this, right? So, if that's the case, but we see that when we actually draw it, it actually comes nearer to 0, then what's actually happening? Because remember, your x-intercept is when x is, or y is, equals to 0. If y is equals to 0, and we have just seen when we try to solve for x, that it is impossible to solve for x. It is telling you that it will not touch the x-intercept, right? This graph will not touch the x-intercept. But when we go back to our table method, we can see that all these numbers, if we continue to -7, -8, -10, negative, etc., and kept going closer to negative infinity, this number would become 0,00000000000. It will just seem to always come nearer and nearer and closer and closer and closer to 0. That's why when we say y tends to 0 when x tends to negative infinity. So when these numbers get smaller, our x values that we put into our function get smaller, then our y also comes closer to 0. But it's not equal to 0. It comes closer to 0. It's an approximate to 0, right? And that brings this particular word for it. Because y tends to 0, not equals to 0, but because y tends to 0, we call this an asymptote of y is equals to 3x when x tends to negative infinity. So because of this, we know that it tends to 0, right? And this is what we call an asymptote of y is equals to 3x, 3 to the power of x, when x tends to negative infinity. So what basically happens is that we never draw our graph on the x-axis. And this line here, this is this weird color here, this green color, is the symbol. It's showing that this is where the asymptote is, and this is where this graph will never go past, right? And so basically that is an asymptote. Okay, so the domain for this particular function, which is y is equal to 3 to the power of x, is x, which is an element or belongs to real numbers. We've already spoken about it. And the range in this case, it is all values except 0 to infinity, right? And basically that is example 1. Now with example 2, same thing applies. We looked at the same way. As you can see, our a in this case is 2, our b is 3, right? And so that's how we found this particular equation. But now when we have to draw it, this is what we find for the numbers, right? And as you can see, this is how the drawing would look. Now, I know this looks very similar to the one that we have before. But look at this one. The y-intercept was at 0 maps 1. But now the y-intercept here is at, I think it's at 2 maps, 0 maps 2. Yeah, 0 maps 2. Yeah, I say 1 maps 2. Yeah, 0 maps 1 and 0 maps 2. Right. Okay. So, since that is clear, right? What's actually happening? What's the difference here? Before, we had y is equals to just 3 of x. Now, when they added BA, right, which is 2, right? So, now it becomes 2 times all this, which is 3 to the power of x, right? What actually happens to the numbers? They just get bigger or get even more smaller faster, right? As you can see, when we had 0 here, it was 1 for the example, the previous example. But now it's 2, right? Because it's going to be times by 2. So it's 1 times 2. Here, then it's times 2 again. It's 6, it's 18, it's 54. You see, it's 1,458. It increases even faster. It increases even faster when we increase our x, and it decreases even faster, meaning it goes closer towards 0 even faster, right? So that's the difference between them. And as you can see, it looks the same, but it's not the same type of graph. Okay, so when we try and find our y-intercept, as you can see, our f of 0 would give us what? It would give us just that it's 2, and the coordinates would be 0 maps 2. And when we want our x-intercept, same thing happens again. We can't actually solve it. This cannot be solved. This cannot be solved, right? And therefore, what we find is that we actually have what? We have that y tends to 0, and this is what we call an asymptote, right, of this graph when x tends to negative infinity, right? And then the domain obviously will be x for all real numbers, which could also be written as this. So this here is what we call set builder notation, as well as this one. And these two here is our interval notation. Okay, so x is an element of real numbers, or we can just say x belongs to these real numbers. And another way of saying it is that x belongs to negative infinity to positive infinity. And then for range, y belongs to a set. Now when I put these brackets in, it means a set. So y belongs to a set where y is an element of real numbers such that y is greater than 0. So let me read that again. So y belongs to a set where y belongs to the real numbers such that y is greater than 0, right? And basically that is the set. Okay, or we could just would have said y belongs to in between 0 to infinity, and they are not included, and that's it. Okay, so that is basically almost all of it, right? That is the video, but I wanted us to actually look at some differences, graphical examples of the exponential function's behavior when we change a and b, right? Okay, so the first one, when we're comparing it, it's y is equals to 5x compared to y is equals to negative 5 to the power of x. Now, if you look at this, on the left, this graph here is that one, right? And this graph is that one. Notice that when it was positive, it was above the y-axis, right? It was on this side of the y-axis, was on the positive side of the y-axis. But because it is a negative, now it's below the positive y-axis. So be aware, when it's positive, it should be above. It should look above like that. If it's negative, it should look below like that. Okay? Another comparison, as you can see, we have negative 3, right? But since it's a negative outside, it should look below, and as you can see, it looks below. It's on the negative y axis, right? And when it is positive, it's above the y axis. It's positive y values, okay? Negative y values because it has a negative there, positive y values when it's that side, okay? The next comparison, we have 3 to the power of x, and here we have 1 over 3 all to the power of x. Now, what is happening here? We have 1 over 3. Now remember, they said b is in between 0 to 1, right? 0 to 1, right? But we're not including 1 and we're not including 0. But if it's 0 and 1, what are numbers in between 0 and 1? Those are fractions. Fractions like 1 over 3, 1 over 4, 1 over 2, 3 over 5, and so on, right? So those values, we can put them in as b. And as you can see here, we have 1 over 3, which is a fraction, right? So what happens when b is a fraction then? Then as you can see, here it's not a fraction, it's just 3. It moves from the left-hand side to the right-hand side. But now it moves from the right-hand side to the left-hand side. So you see, it swaps the way they go up, right? Whereas this one would go up like that, this one will come up the other way around, right? So be aware, when it's 1 over 3, when b is a fraction, it means that it will go that way, not that way, okay? And here is another example of this case, but now it has a negative, and b is also what happened to be. It is a fraction. So if it is negative and a fraction, firstly, we know when it's negative, it must look down. So it must be below, right? But now, if you think about it, when we move this way and we change this into a fraction, right, to be 1 over 3, then what happens? This would come and cross this side, right? And go like that. And as you can see, it crosses the side and goes like that. And so, those are the comparisons that I wanted you to take note of. This can be very helpful, especially when you need to actually graph their particular functions. Okay, so I hope this has been helpful. It's been a very long video, but I think this has been helpful. Please listen to the video as much as you can, as many times as you can, so that you may understand my meaning. And whenever you have any questions on the video, please feel free to ask your tutor. Please, 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 don't be afraid to ask your tutor about the video, and they will explain perfectly what was meant, and if there's a mistake, they will also explain it further. Okay, so other than that, I really hope that your studying is going well, and I hope this will help your individual study. So I will see you next time.